All right, looks like we can continue on with integration. Maybe I'll open up the chat so I can keep an eye on that. There we go. All right, so here in theorem 6.2.4, what we're doing is we're taking a look at the opposite direction of the previous theorem that we looked at. So refer to theorem 6.2.3. What we're doing is we're just working the opposite direction. So we defined the natural log function, natural log of x, to be the integral from 1 to x of 1 over t dt. This is how we defined it. So what we're looking at now is we're looking at the indefinite integral of 1 over x. So if we consider the derivative d over dx of this, then we are looking at the derivative of the natural log function, which gives us the 1 over x. So that's excellent. So we want to look at this theorem. Where did we go here? In reverse. Now, when I integrate both sides, the integral of a derivative gives us back the original thing. So integral of the derivative of natural log is just natural log. And that would be the integral of 1 over x. Now, in our theorem in 6.2.4, it talks about the natural log of the absolute value of x. So here we just use x, and the derivative of x is 1, and u is x. So the integral of the natural log of the absolute value, integral of the derivative gives us back natural log of the absolute value when we integrate 1 over x dx. Then we want to be able to talk about essentially the substitution, right? What would a substitution look like? And the substitution would just look like us using u instead of x. That's all. So that's how we get these. This is our specific integral of 1 over x. And when we have 1 over u, right, this is referring to a substitution. That's essentially what we should see every time. We either have 1 over x or we have 1 over u. All right, so let's take a look at some examples of this. Again, right, this is just the reverse direction. When we take the integral of 1 over x, it gives us the natural log. So if we recognize it, we can pull out the multiple of 4 here. That gives us the integral of 1 over x dx. And we immediately have, right, the integral of 1 over x dx is the natural log function. So this is 4 times the natural log of the absolute value of x plus c. You could leave your answer right here. This is okay. What we could also do, we could do one more thing. We can make use of the properties of logarithms. So this is okay. This is good. This is absolutely fine. We could make use of the properties of logarithms to recognize that this is the natural log of the absolute value of x to the 4th power. But beyond that, if we're taking the absolute value and raising it to the 4th power, then these absolute values are essentially useless. So this is just the natural log of x to the 4th plus c. Now we don't even have any absolute values. So that looks really good. So this is a fine answer right here. I like this one. This answer is also good. All right. So of course, that was a relatively basic example. We want to take a look at a slightly more interesting one. So now we have polynomial divided by polynomial. And again, this is actually very conveniently a simple example. What I might notice is I have a degree 3 polynomial in the denominator and a degree 2 polynomial in the numerator. And when I have this situation, sometimes it is as simple as this one, or it can be manipulated to be as simple as this one, where we can notice that the numerator is exactly the derivative of the denominator. Derivative of 2x cubed is 6x squared, right? Bring the 3 down as a multiple. 2 times 3 is 6. Reduce the power by 1 to be x squared. Similarly, derivative of x squared is 2x. derivative of a constant is 0. So if I try to make this as explicit as I can in our substitution, right, would I always expect to see a substitution? Maybe not. But in this case, it's nice to make it explicit. So let's let u be equal to 2x cubed plus x squared minus 17. Then du is equal to 6x squared plus 2x dx. And now we can perform a substitution. So this integral itself is equal to, right, we have 6x squared plus 2x times dx. So this is the integral of 1 du, right? This times dx just gives us du, and the denominator is u. Simple as that. The integral of 1 over u du is the natural log of the absolute value of u du. No more du there, sorry, plus c. We took an integral. Did I do that up here? Yeah, plus c, it's there. And then we substitute back. Natural log of the absolute value, u is this polynomial, 2x cubed plus x squared minus 17. And don't forget about b plus c. All right. So for our first two examples, relatively straightforward in terms of just almost explicit applications of the theorem 1 and 2. 1 and 2. We had to pull out a multiple of 4 in the first case, and we had to observe the substitution in the second. But otherwise, this is exactly it. All right, that's 1 and 2 are 1 and 2 up there. So we want to make things a little bit more interesting. So let's do that. In this case, we want to find again the indefinite integral, but we no longer have a numerator that is 1 degree less than the denominator. That is, we clearly, the numerator is not the derivative of the denominator. So it's not u prime divided by u. So what do? Well, here we follow directions. We find the indefinite integral by using long division. If you're familiar with synthetic division, you're welcome to use synthetic division as well. Both are absolutely fine. I'll present both in this case, just so we can say, all right, we saw both ways there, because it can be very helpful. Let me see here. I want to make sure that I copied it or I write it down correctly. So let me see what I have. I have this division written down. Okay, here we are. So polynomial division. I'm going to go with a different color here. We'll go with black. So that way, this is our scratch work. This is our side work. This is our preparation for actually trying to calculate the integral. So what do? We have long division of polynomials, x plus 5. And what are we dividing? We are dividing x cubed. Now, long division of polynomials or synthetic division, whichever case you're going here, you need to make sure you remember that we have 0x squareds. Don't forget about that. X cubed to x, 0x squareds. So then minus 6x minus 20. So when we perform long division of polynomials, this is very similar to long division of numbers. How many times can we get the divisor to go into the dividend? Yep, I think that's the right words. Anyway, this is definitely a divisor. So how, excuse me, but in this case, what are we thinking of? What we can do is we can say how many times does x go into x cubed? X squared times. So then I end up with x squared times x plus 5 is x cubed plus 5x squared. And that's what I'm subtracting here, x cubed plus 5x squared. So I subtract that, x cubed minus x cubed, 0 minus 5x squared. Bring these down, negative 6x minus 20. And then I ask myself, how many times does x go into negative 5x squared? That would be a negative 5x times. Negative 5x times x is a negative 5x squared. The number that I'm looking for, negative 5x times 5 is a negative 25x. So I'm subtracting this quantity. Negative 5 minus negative 5 is 0. That's what we're looking to have happen. Negative 6 minus a negative is negative 6 plus. So negative 6 plus 25 gives us 19x. Bring down the negative 20. And then how many times does x go into 19x? It goes in 19 times. Nineteen times x is just a 19x. 19 times 5 is, let's see here, 95. So I'm subtracting 19x plus 95. 19 minus 19 goes away. Negative 20 minus 95 gives us a negative 115. So that is long division of polynomials. If it's something that you don't recall or are unsure if you've seen it before, I would encourage you to simply go to YouTube and type in long division of polynomials or look up synthetic division. You won't always be able to use synthetic division, but you can in this case. When you're dividing by x minus something, then you can use synthetic division. So if I recognize here that I have, this is x minus a negative 5, then I'm using negative 5 as my number for synthetic division. In synthetic division, we just copy down the coefficients of the original polynomial, 1, 0, negative 6, and negative 20. Again, if you're not familiar with this and you have no idea what I'm doing, that's absolutely fine. You don't need to know synthetic division. For those of you that do know it, it's just a nice reminder. Bring the 1 down. 1 times a negative 5 gives us negative 5. And then I add these two numbers. So this, we get this number by taking that one and multiplying it by that. 1 times negative 5 is negative 5. 0 plus a negative 5 is negative 5. Negative 5 times a negative 5 is a positive 25. Negative 6 plus 25 is 19. 19 times a negative 5 is a negative 95. Negative 20 plus a negative 95 is a negative 115. So much like we used these as the coefficients from, or these were the coefficients from the original polynomial, what we're left with is the coefficients of the resulting polynomial. Let's see here, x squared. Actually, let me put that in black still. X squared minus 5x plus 19, which is the same thing we have here. This number here is called the remainder. This number here, same thing, it is the remainder. But what is important about this is that our integral of, let's see here, x cubed minus 6x minus 20 divided by x plus 5 dx becomes the integral of x squared minus 5x plus 19 minus 115 divided by x plus 5. So our integral is much easier now. Integral of x squared is 1/3 x cubed. Integral of negative 5x is negative 5/2 x squared. Integral of 19 is 19x. Integral of 115 over x plus 5 this is going to give us, right, this is negative 115 times 1 over x plus 5. So this is actually going to give us negative 115 times the natural log of the absolute value of x plus 5. And then add our constant at the end. And that's it. So the integral has become very easy after performing the long division or synthetic division. All right, that takes us just over the time that we want to get out of here. So thank you for your time and attention today. If you have any questions, feel free to stick around. Otherwise, watch for the videos to be posted tomorrow for you guys to watch. And I'll see you again on Friday.